Hello everyone. The title of this video is Graphing Hyperbolas Not Centered at the Origin. Alright, so in this video I'm going to be doing examples that are taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 12.2, called the Hyperbola. I'm under the heading Graphing Hyperbolas Not Centered at the Origin. And each example I do will either be an example from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Alright, so again I'm going to be assuming some information from you, prior knowledge. This section of the text comes after graphing hyperbolas that are centered at the origin, and I put out a video on that, graphing hyperbolas centered at the origin. So if I'm assuming you've seen that or at least read through that in this, because this is very, very similar. I don't want to spend as much time on this. The only difference between graphing hyperbolas not centered at the origin versus centered at the origin is just where the center is. Everything else is the same. Maybe the equations of the asymptotes will be a little harder to find, but you should know how to find equations of lines by now anyway. So yeah, so instead of x, we have the x replaced by x minus h, and y are replaced by y minus k, and then I'll shift the center from the origin to the point h comma k. Right, and they have this whole thing here about the different versions of the standard form pardon me, for an equation of a hyperbola. One is x minus h squared over a squared minus y minus k squared over b squared equals 1. And this is one, when the x squared term is first, the transverse axis is horizontal. The curves of the hyperbola will open left and right, or the vertices and the foci will be left and right of the center. Now if you switch it, if you have the y squared term first, y minus k squared over a squared minus x minus h squared over b squared equals 1. If the y squared term is first in the standard form, then the transverse axis is vertical, right, parallel to the y-axis. And in this case, the curves of the hyperbola will open up and down. The vertices will be above and below the center, the foci above and below the center, and so on. All right, they have some pictures down here. No, they don't. I think their pictures are earlier. But anyway, so like I said, if you remember how to graph hyperbolas centered at the origin, this isn't too much different. And all the letters mean the same stuff. The A represents the distance from the center to a vertex. B represents the distance from the center to a co-vertex. C represents the distance from the center to a focus. Right? And c squared was equal to a squared plus b squared, right? Or c was plus or minus the square root of a squared plus b squared. But c squared equals a squared plus b squared. That was the relationship between c, a, and b for all hyperbolas. Okay, so I'm just going to get into it. All right, and then we'll be graphing these, right? And each one of these we're asked to graph the hyperbola. And while I'm doing that, we'll identify and label the center, vertices, co-vertices, foci, and asymptotes. Alright, so this first example I'm given starts off with the y squared. It has the y squared term minus the x squared term. So this is in that standard form where you have the square divided by a number minus the square divided by a number equals 1. So this is in this form here, y minus k squared divided by a squared minus x minus h squared divided by b squared equals 1. Right? It's in that form here. So, and when we graph this, right, the curves should be opening up and down, right? The hyperbola will look like this. The transverse axis is vertical, right? Wherever the center is, the vertices are above and below the center. Right? All right, well, the center should be the easiest thing to identify if the equation is in standard form, like this one is here, h comma k. But you just gotta pay attention though. Don't too often people will say, oh, this is y plus 4, so y equals negative 4. That negative 4 will be, the value of k, because plus 4 is minus negative 4. And x minus 3 is, x minus h is 3. But too often people just go left to right and go, oh, negative 4 and 3. They'll say the center is negative 4, 3, but that's not the case. You have to pay attention to what's with what. What's with the x, what's with the y. 3 is with the x, right? If x were 3, you'd have zeros. And again, a shortcut way of thinking about this is what's the value of x and what's the value of y that would just give me 0 over here? So 3 for x, negative 4 for y. There's your h and k. There's your center. All right. And I'll start on a separate piece of paper making a rough sketch of this. All right. I'm just making an xy plane. And the center I just said was at 3, negative 4. So 3 for x, negative 4 for y, right, and a little dot there. There's the center. Right. Now remember, the center is not on the hyperbola. The center does not solve the equation or satisfy the equation. Right, if you were to put in 3 for x and negative 4 for y, as I mentioned, this side would be 0. You'd have 0 equals 1. That's false. So the center is more of a guiding point, but not a solution. All right, then under this first denominator, the denominator with the positive coefficient is 100. That's going to be the value of a squared. And if a squared is 100, then a is 10. And remember, the vertices are going to be above and below center. The transverse axis is vertical here with this leading y squared. So we can, once we know the center and the value of a, you can then say where the vertices are going to be. So it's going to keep the same x-coordinate, right? If I'm going to go above and below the center, I need to add and subtract 10 to the y-coordinate of the center. So negative 4 plus or minus 10. All right, so the two vertices then are 3, 6, and 3, negative 14. Right? Negative 4 plus 10, negative 4 minus 10. But that's 10 units above and 10 units below the center. All right, so back on my page here with the graph. From the center, I go 10 units up to 3, 6. 3, 6. And again, I'll label this. This is a vertex. That's a vertex. And that is a point on the graph. And so is the other one, right? And from the center, I go 10 units down. Sorry, this is going to be not that great looking. So negative 14. So 3, negative 14. Yeah, this might be a bad drawing because we won't get a lot of it in here. Because there's going to be a curve opening up and a curve opening down. You're not going to see a lot of this curve opening down. I must apologize for that. There's no lack of foresight on my part. But those are the vertices, right? Here's another vertex. And again, those are solutions of the equation. If you plug in 3 for x, that makes this second term 0. And then plug in 6 for y. You'd have 10 squared over 100. That's 100 over 100. That's 1. 1 minus 0 is 1. That's true. And then plug in 3 for x and negative 14 for y, and you'd get the same thing. You'd get 1 minus 0 equals 1. All right. Now the other denominator, the denominator under the negative term, right, the term with the negative coefficient, that's the b squared, 64. Right, so b must be 8 then. Now if the vertices are above and below the center, the co-vertices, which are not on the hyperbola, will be to the right and left. So the co-vertices, right, so I'm going to take the coordinates of the center, 3, negative 4, but I'm going to add and subtract 8 to the x coordinate, right, to move it right and left. So the co-vertices are be 11, negative 4, and negative 5, negative 4. And I'll plot those. But not in the same color as the vertices, though. So from the center, I go right 8 to 11, negative 4. All right, there's a co-vertex. I'm just going to put CV for co-vertex. I didn't make it very big, right? It's not actually a solution. And you can check it out. Plug in 11 for x and negative 4 for y, and the equation will not be true. All right, you can check that out yourself. So I went 8 units right and now 8 units left to negative 5, negative 4. Right, there's the other co-vertex. Again, not a solution. What the co-vertices are used for, along with the vertices, is to make a little rectangle. That'll help me draw the asymptotes. So I draw a rectangle that contains, the vertices and co-vertices. And it's a dotted rectangle, right? Because the rectangle isn't part of the hyperbola either. Right, so I don't want to make a solid rectangle. All right, and then through the corners of these, also through the center, should go the asymptotes. Probably should have used a ruler the whole time, but right, through the corners of this box. Sorry, again, that should be extending down further. There should be more of this. There's one asymptote with a positive slope, and then this other asymptote with a negative slope, again going through the center and the corners of this rectangle. All right, so something like this. Now, I know you know how to write equations of lines, so I'm not getting into how to write equations of lines. I'm just going to write it. So the equation of this asymptote with a positive slope, well, the slope is easy enough. Just go from the center to one of the corners, right? That'll tell you the slope. Do rise over run. Remember, I went up 10. That was A, and then B was 8. Up 10, right 8. The rise is 10, the run is 8. So the slope is 10/8 or 5/4. But it's not just 5/4 times x. What I'm going to do is I'm going to use point slope form here. Y equals 5/4 times, and then x minus 3, right? X minus the x coordinate of the center. And then afterwards, to get it to negative 4, minus 4, right? With the plus k. So the equation of this line coming from point slope form. And if you want to distribute the 5/4 and get it in mx plus b form, you can. The slope intercept form, you can. But this is nice here because then the other line is the exact same equation but with a negative slope. This other asymptote is y equals negative 5/4 times the quantity x minus 3 minus 4. And again, I'm not going to go into how to write equations of lines. That's not what this is about. You should know how to do that. So now that I have the asymptotes and the vertices in, you should be able to draw a rough sketch of the curve of the hyperbola. So from a vertex, and using the box, using the rectangle and asymptotes as a guide, just draw these curves that'll approach the asymptote as you move further away from the center. So there's one curve of the hyperbola, one branch. And then down here, again, I'm very sorry about this. I wasn't seeing clearly, but the other one should be doing the same thing. Very tiny amount of it. It basically looks like this top curve, but reflected across the line y equals negative 4, the conjugate axis. Okay. Alright, so I got the asymptotes, the equations for the asymptotes, got the vertices, the center, the co-vertices. Now we're also asked to label the foci. Now remember, for the foci, you need that value of c, right? But to find c, right, the relationship between c, a, and b for any hyperbola is c squared equals a squared plus b squared. Right, and a squared is 100 plus b squared is 64. So this is 164, meaning that c is, the square root of 164. And 164 is 4 times 41. So this is 2 times the square root of 41, square root of 4 times square root of 41 if you want to simplify it. But this helps me find the foci then, right? So the foci, which again are on the transverse axis, they're on the same line as the vertices. The vertices were above and below the center. The foci will be above and below that, right? They're surrounded by the curves. So I just take the coordinates of the center, right, 3, -4, but I'm going to be adding and subtracting this 2 root 41 to the y coordinate of the center. Right. And this is between 12 and 13 units here. So I'd be basically taking the center and going up between 12 and 13 units. So there's 10 and then 11, 12, 13, so 7, 8, 9. So somewhere between 8 and 9 is -4 plus 2 root 41. And that's where one of the foci is at, one of the foci is at. There's a focus of the hyperbola. And then there'd be a focus down here too. I am so sorry. But there's another focus down here that's also, you take -4 minus 2 root 41, and there'd be the other focus. Right, and again, the y coordinate here would be -4 minus 2 root 41. That's a terrible drawing. This is a terrible drawing. I apologize. Now, the whole reason that you have to find these foci is because of how a hyperbola is defined. What makes a hyperbola special, what makes these two foci, these foci special, is if you were to take any point on the hyperbola, any point at all, any point on that curve, any point on that curve, and take the distance to one focus, I call that D1, and then the distance to the other focus, so that should be more straight, call it D2, the difference in those distances is always going to be 2 times whatever A is. And A was 10, so this is 20 all the time. So no matter what point you pick, you can find any other coordinates on these curves that you want, find the distance to one focus, the distance to the other focus, and subtract those distances. Take the large one minus the small one, and you'll always get 20. Right? That's the special thing about these foci. Right? That's how a hyperbola is defined. Okay, great. So that was everything. Right? I had the asymptotes, the foci, co-vertices, vertices, center. Cool. Now what I want to do is go to Desmos. Right? It's a free online graphing calculator at desmos.com, and then just compare my graph to a better looking graph. But I just want to make sure that I have the right vertices and the right asymptotes, and that the curves are opening up and down the way I have in my drawing. Alright, so the equation they gave us was this. The quantity y plus 4 squared divided by 100 minus the quantity x minus 3 squared divided by 64 equals 1. And here it is. See the curves opening up and down there. There's the two curves of your hyperbola. And I said the vertices were at 3, 6, and there's 3, 6. Look at that. And the other vertex I had was at 3, negative 14. Hey, all right. So it looks good so far. The center, right, should be at the point 3, negative 4, but I'm not going to plot that because if those are the vertices, then 3, negative 4, oh, maybe I should plot it. 3, negative 4 is the center. Right, clearly that point's halfway between these two. And then I'm going to draw the asymptotes, right, the equations of my asymptotes. Y equals, one had a positive 5/4 slope times x minus the x coordinate of the center plus the y coordinate of the center, right? And then the other one, well, I'll just copy and paste this and change the slope to negative 5/4. And I'll make those the same color and dashed because they're not actually part of the hyperbola. There we go. See how they both run through the center like this. One has a slope of positive 5/4, the other one has a slope of negative 5/4. And yeah, it looks like the curves on the hyperbola approach these asymptotes as you move further away from center. Another way to test that too is zoom out. If I zoom out, you'll see that the hyperbola curve will pretty much get really, really close to becoming the asymptotes. Right, if you zoom out far enough, it looks like that curve is becoming those asymptotes. It doesn't actually touch them. Right? If you zoom in close enough, you'll see the hyperbola doesn't actually touch the asymptotes, but it gets really, really close to them. Right, so these asymptotes look like they're good. So my equations of the asymptotes are good. The vertices were correct. The center was correct. My drawing was correct. Even though it was a crappy looking drawing, it was still a valid drawing, a valid graph of that equation. Okay. And this is what we're doing. Right? But the key is, though, to get the equation in this form, one of these forms, with the y minus k here, x minus h here, or with the x minus h here, y minus k there. But our goal is to get the equation in this standard form. Now, number one, it was given to us in standard form. In my next example, it's not. So this is actually an equation of a hyperbola. This is actually the equation of a hyperbola. It just doesn't look like it, right? This is clearly not in standard form. All right, now the standard form, notice I have a positive x squared term and a negative y squared term. So I'm probably going to get the form to look like this eventually, where the x squared term is first, x minus h squared over a squared, then the negative y squared term minus the quantity y minus k squared over b squared equals 1. This is what we want. Right, we want this. We want standard form. So here's what we're going to do. All right, if you're given an equation, this is sometimes referred to as the general form, where everything's on one side, zeros on the other. You're going to transform an equation like this into standard form by completing the square. All right, now again, this isn't a lesson on completing the square. I'm assuming you know how to complete the square on expressions already. We're going to complete the square on the x's and y's. So the first thing I'm going to do is actually gather the x terms and y terms near each other. So I'm just going to shuffle some terms around here. We have 9x squared, and then the other x term is minus 36x, and then the y terms, minus 4y squared, minus 40y, and the only term I'm really not concerned with when I'm trying to complete squares is the constant term. So this negative 388, I'm going to add to the other side. So equals 0 plus 388 is positive 388. Okay, now, remember to complete this, now we'll do these separately, the x's and the y's. Remember to complete the square, the coefficient of the square term had to be positive 1. Well, the coefficient of x squared is positive 9, not positive 1. But that's easy to fix. If I want the coefficient of x squared to be positive 1, just factor out 9 from the x terms. So from the x terms, I'm going to factor out 9. And then the same thing with the y terms. The terms that have y in it, the coefficient on y squared is not positive 1, it's negative 4. Right, don't forget the negative is part of the term. So easy fix, from the y terms, I'm going to factor out a negative 4. So that leads me to this line. So again, from the x terms, I factor out 9. Now if I factor out 9, the remaining factor would be x squared minus 4x. Now the coefficient on x squared is 1. So inside the parentheses, I'm going to be able to complete the square. So I'll leave some space for that number we're going to add to complete the square, and then close the parentheses. Same thing for the y terms. If I factor out negative 4, so I pull negative 4 out. Now if I do that, we'd have y squared plus 10y. And now the coefficient of y squared is 1. So I can complete the square on the y's. I'm going to leave some space for that number we're going to add to complete the square. Alright, and then the other side I haven't touched, so equals 388. Alright, now comes the completions of the squares. X squared minus 4x. Remember how to complete the square. Pardon me. You take half the linear coefficient, which would be negative 2, and square that. It would be positive 4. So inside the parentheses, I'm adding 4. But you got to remember it's an equation. You got to keep things balanced. Now, many people make this mistake. If I add 4 in here, you don't just add 4 on the other side. You got to remember, you got to think about what you factored out. If I add 4 inside these parentheses, if you were to redistribute that 9, you'd have 9x squared, cool. You'd have your minus 36x. And then the plus 4 here, times 9 would be plus 36. 9 times 4. So adding 4 in the parentheses really adds 36 to that left side. So I must add 36 to the right side. All right, this is the 4 that I added times the 9 that I factored out. And then in a very similar fashion with the y's, y squared plus 10y. Complete the square. Half of 10 is 5. 5 squared is 25. So I'm adding 25 in the parentheses. But I take that 25. Remember what we factored out? We factored out negative 4. Negative 4 times 25 is negative 100. So I'm putting a negative 100 really over on the left side. So I need to do the same on the right. Negative 100 minus 100. So you got to keep in mind, right, 25 times negative 4. The number I added times the number that was factored out. Right. Now it's balanced. Now the whole reason these numbers get added, the plus 4, the plus 25, is so you can have a perfect square trinomial. All right, so on the left side we have 9 times, and then this x squared minus 4x plus 4 is the quantity x minus 2 squared. All right, and then minus 4, and then times, and then this here y squared plus 10y plus 25. That's the quantity y plus 5 squared. Equals, and then the other side, 388 plus 36 would be 424, minus 100 would be 324. So we're almost there. I'm almost in this form, this standard form. Notice on the right side of standard form it's equals 1. Equals 1, not equals 324. So a way to fix that, to get this to be in standard form, is now divide everything on both sides, all the terms, by 324, whatever this number is over here. Right, because anything divided by itself will become 1. Now 9 does go into 324 evenly, right? It goes into it 36 times, right? 9 times 36, that'd be 270 plus 54, 324, yeah. So this first term becomes x minus 2 squared divided by, and then 9 goes into 324 36 times. Minus, and then 4 goes into 324 81 times. So this would reduce to y plus 5 squared over 81 equals 1. And here we go. Now I'm not done yet. We still have to graph it. I know you're probably thinking, man, that's a lot of work for this, and then we still have to graph. Yeah. Sorry to say. But now we have the equation in standard form. And now it becomes just like the last example. The first example I did in this video, the equation was already in standard form. And I just found the center and the vertices, co-vertices, asymptotes, all that. So we're doing that here. And it's in standard form for a hyperbola that's going to be, have a transverse axis that's horizontal. The curves are going to open to the right and the left. The vertices and foci will be to the right and the left of the center. Right, because it's starting with x squared minus the y squared. Alright, so the center once you're in standard form, a lot of things should be easy to identify. The x coordinate of the center would be positive 2. The y coordinate of the center would be negative 5. The value of a squared, right, that first denominator under the positive term, is 36. So a must be 6. And remember, the vertices are to the right and left. So I'm adding 6 and subtracting 6 to the x coordinate of the center for the vertices. So 2 plus or minus 6, comma, and then the same y coordinate, right, negative 5. Well, I mean, that would be 8, negative 5, and negative 4, negative 5 for the vertices. And these should be solutions, right? Remember, the vertices are solutions of the equation. You go to this equation in standard form, or even if you went back to the original equation, that weird one, the way it was originally given to us, put in these coordinates, and it should make the equation true. All right, so we got vertices. B squared is the other denominator, right? 81. So B is 9. And then the co-vertices, right? Instead of adding to the x coordinate of the center, I'd be adding to the y coordinate of the center. So 2, comma, and then negative 5 plus or minus 9. So 2, 4, negative 5 plus 9, and then 2, negative 14. Right. And let me start drawing this actually. All right, let me start drawing this. All right, so center at 2, negative 5. I'm going to make the spacing a little smaller this time. Pardon me. So there's the center. Then I go right 6, left 6 for the vertices. So there's 8, negative 5 for one vertex. and then -4, -5, -4, -5 for the other vertex. The co-vertices, I'm going up and down 9 units. So from the center up 9 would be at 2, 4. Right, there's a co-vertex, and then down 9 to 2, -14. And now that I have the vertices and co-vertices in, I can make this rectangle. That'll help me draw the asymptotes right through the corners and through the center. So there's one asymptote, the other asymptote. Pardon me. And the equations of the asymptotes, this one up here would be y equals, now the slope, again, just go from the center to a corner. That'll tell you the slope of one, and then the slope of the other one is just the opposite. So remember, my rise here was 9, that was b, and the run is a. This is b over a, so 9 over 6. But 9 over 6 reduces to 3 halves. So y equals 3 halves times the quantity x minus 2, right? X minus the x coordinate of the center, and then plus the y coordinate of the center, so minus 5 there. So that line has equation y equals 3 halves times x minus 2, and then minus 5. And the other one has the same equation, but just with a negative slope. Y equals -3 halves times the quantity x minus 2, and then minus 5 after. Those are the asymptotes. And now that I have the vertices and the asymptotes in, we can make a rough sketch. Just from the vertex, draw some curve that will approach these asymptotes as you move out away from the center. So there's one curve. Here's the other curve for the hyperbola. And then finally the foci, which we need the value of c for. Now c squared is again a squared plus b squared for all hyperbolas. And here that's 36 plus 81. Right? So that's 117. Right? 36 plus 81. So c is the square root of 117. Now 117 is 9 times 13. So this is 3 times the square root of 13. And this is getting, just like for the vertices, I'm going right and left for the foci. So the foci are, you're going to be adding this and subtracting this value from the x coordinate of the center. So 2 plus or minus 3 root 13 comma -5. Now the square root of 117 is between 10 and 11 units. So that was what, 6 units, right? And then 7, 8, 9, 10, 11. So 9, 10, 11, 12. So between 12 and 13 on the x-axis is 2 plus 3 root 13. And then, something between 10 and 11 units to the left. 6, 7, 8, 9, 10, 11. In between -5, 6, 7, 8, 9. -8 and -9. Somewhere between -8 and -9 is 2 minus 3 root 13. And here are your foci. All right, so 2 plus 3 root 13, comma, -5. Right, there's a focus, and 2 minus 3 root 13, comma, -5. Right, on the same line with the vertices, right, that transverse axis, there's another focus. Right. So yeah, that was a long one. Right, because I had to change the equation to standard form first, and then do all the usual stuff that I did in example 1. All right, and once again, the reason we find the foci, you could take any point on this curve, or any point on this curve, right? Any point on the hyperbola, take the distance to one focus, call it d1, the distance to the other focus, call it d2, and subtract them. Take the larger minus the smaller, or just do the absolute value of their difference, and it will always be 2a, which in this case, a was 6, so it'll always give you the number 12. Right, for this particular ellipse, if you take any point on the sorry, I keep saying ellipse. For any point on this hyperbola, take any point on this hyperbola, the distance to one focus, the distance to the other focus, subtract them, it'll always be 12. Right. I apologize if the equations for ellipses and hyperbolas are so similar, and sometimes I mess the words up, but know that I mean hyperbola, even if I say ellipse. Okay, and then let's just double check this. Now what I'm going to do to check this one is just kind of enter the equations for both the equation we started with that wasn't in standard form and the equation that we ended with in standard form, and see that they're the exact same equation. All right, so back to that Desmos site. Just clearing all this out. All right, so the equation we were given, 9x squared minus 4y squared minus 36x minus 40y minus 388 equals 0. And you see this hyperbola. You see it showing up. All right, look at that. All right, and then I'm just going to graph the other equation, and you'll see it's the exact same picture. Right, it's going to be right on top of this one. The equation we ended up with after changing it to standard form was x minus 2 squared divided by 36 minus, and then the quantity y plus 5 squared divided by 81 equals 1. And look at that. I'm going to turn it off and on here. You will see it's the exact same picture. All right, can you see it popping up right on top of the other curve? It's the exact same picture. Same center, same vertices, same asymptotes, everything. Okay, great. So moving on. Got another example here where it's already in standard form, so this should be a lot quicker. So it's already in standard form. The x squared term is first minus the y squared term, so it's going to be another one where the transverse axis is horizontal, right, like this, where the foci and vertices are on a horizontal line. They're to the right and left of the center. And if it's in standard form, again, the center should be easy to identify. It's just 2 for the x coordinate and negative 3 for the y coordinate. All right, and I'll start plotting this stuff over here. I'm going to go a little quicker than the first couple examples, of course. So 2, negative 3, right there's the center. The value of a squared is 8. So a is the square root of 8, which is 2 times the square root of 2 when you simplify it. So the vertices are at, now remember they'd be to the right and the left of the center, so I'm adding and subtracting this value to the x coordinate of the center. So 2, and then plus or minus 2 root 2, comma, negative 3. Now the square root of 8 is a little less than 3 units, so here's 1, 2, 3. So somewhere between 4 and 5 is 2 plus the square root of 8. And then, again, from the center left square root of 8, 1, 2, 3. Somewhere between negative 1 and 0 is 2 minus the square root of 8. So we got these vertices here, vertex and a vertex here just to the left of the y-axis. Alright, then b squared is the other denominator under the term with the negative coefficient, right? And that is 27. So b is the square root of 27, which reduces or simplifies to 3 times the square root of 3, right? It's 9 times the square root of 3. And so I can find the co-vertices, which will be above and below the center, right? So I can take the coordinates of the center, and I'm just adding and subtracting this to the y coordinate. 2 and then negative 3 plus or minus 3 root 3. Now the square root of 27 is a little more than 5, right? It's between 5 and 6. So from the center, if I go up 5 units, 6 units, that's between 2 and 3. This is really cluttered, right? So there's somewhere between 2 and 3 is negative 3 plus 3 root 3. And then 1, 2, 3, 4, 5, 6. Somewhere between here, between -8 and -9, somewhere between there is the other is -3 minus 3 root 3. There's the other covertex. And then using the vertices and covertices, I make a rectangle. And then through the corners of that rectangle and the center, I draw the asymptotes. And the equations of these asymptotes, this one would be y equals, remember the rise this time is b and the run is a. So it'd be 3 root 3 divided by 2 root 2 for the slope. 3 root 3 divided by 2 root 2. And if you want to rationalize this and make this 3 times the square root of 6 divided by 4, you can. That's the slope times, and then x minus 2 minus 3. There's the equation of that line. And then the other one just has the opposite slope, y equals -3 root 3 over 2 root 2 times the quantity x minus 2 minus 3. Right? Same equation, just a negative slope. Now that I have the asymptotes and the vertices in, I can make a rough sketch of the graph. Right, here's your curve. And really wide curve here approaching these asymptotes as you move out. There's the hyperbola. Right, those two curves. Again, it's a hand drawing. It's not perfect. But there should be one opening right, one opening left. And then for the foci, I need c. C squared is a squared plus b squared, 8 plus 27. 8 plus 27 is 35, right? So c is the square root of 35, which is, a little less than 6. So the foci here are, again, I take the x coordinate of the center and add and subtract the square root of 35. Keep the same y coordinate, that's right and left of center. So a little less than 6. So the x coordinate of the center was 2, 6, 7, 8. So a little less than 8 will be the x coordinate of one focus. Let's say f for focus there. And then 2 minus 6 would be -4. 1, 2, 3, 4. And then a little bit to the right of -4 would be 2 minus the square root of 35. And there's the other focus. And again, the whole setup is, if you were to take any point on the hyperbola, anywhere on the curves, take the distance to one focus, the distance to the other focus, and subtract them, it would always be 4 times the square root of 2, whatever 2a is. And there we go. And I'll leave it to you from here on out to check on Desmos. Graph this equation on Desmos, see if the vertices match my vertices, and see if put in the equations of the asymptotes and see if the curve follows those asymptotes as you zoom out. But I'll leave that to you from here on out. Okay. All right, then I have another equation that's not, it's just like example 2, where it's not in standard form. Right, it's in this crazy general form here. Now notice how there's a positive y squared and a negative x squared. Right, so I'm going to put them in that order, y squared minus x squared. And we're going to get a hyperbola like this. We're going to have a hyperbola where the vertices and the foci are above and below the center. The transverse axis is vertical. So I'm going to rearrange these so that the y terms are first, because it's positive y squared, positive 16y squared, then minus 32y, and then put the x terms next because you have the negative x squared there, minus 4x squared minus 8x equals 52. I'm going to add the 52 to both sides, get rid of that constant term. Alright, then I want to complete the square on the y's and the x's, but I can't do that right now. Because the coefficient on y squared is 16. So from the y terms, I'm going to factor out 16. And the same thing for the x's. I can't complete the square right now, because the coefficient on x squared is not 1, it's -4. So I'm going to factor out -4. So if I do this, we'll have 16 times the quantity y squared minus 2y. And then I'll leave some space so I can complete the square on the y's inside the parentheses there. Then pull out negative 4, so we got minus 4 times, and then x squared plus 2x, right? Because negative 4 times 2x would be negative 8x. And then leave some space to complete the square on the x's, right? Equals 52. Now comes the completing the squares part. And again, you got to remember what you factored out so that you can know what to add to the other side and keep it balanced. For the y's, I'd be adding 1 in here to complete the square on the y's. But if I add 1 in here, 16 times 1 is 16. That's really adding 16 to the left side, so I have to add 16 to the right side. And then for the x's, x squared plus 2x, I would be adding 1 to complete the square. And again, adding 1 in here. But don't forget what you factored out. Times negative 4 would be like adding negative 4 to the left side, so I got to add negative 4, subtract 4 from the right side. Now I have some perfect square trinomials. We can write them as squares. So this is 16 times, y squared minus 2y plus 1 is the quantity y minus 1 squared, minus 4 times, and then x squared minus 2x, plus 2x plus 1 is the quantity x plus 1 squared, equals, and then 48 plus 16, or 68 minus 4 is 64. 64. And then to get it in standard form, remember I need that square minus square equals 1. So now I'm dividing everything by 64 to get 1 on that right side. First term on the left, we have y minus 1 squared divided by, and then 16 goes into 64 4 times. So that becomes 4 in the denominator. Minus, and then here we have the quantity x plus 1 squared. And then 4 goes into 64 16 times. And equals 1, right? And here we go, right? This is the equation, the same exact equation that I started with in standard form. And now I'm going to go about graphing it. All right, so the center would be, now pay attention to what's with x and what's with y. The x coordinate of the center would be negative 1. The y coordinate of the center would be positive 1. Right. A squared is that first denominator under the positive term. Right, so a squared is 4, meaning that a is 2. And we can tell you what the vertices are. Now this time the vertices are going to be above and below the center. So I'm going to add 2 and subtract 2 from the y coordinate of the center. So we have negative 1, 3, and negative 1, negative 1. Right, adding 2 and subtracting 2 to the y coordinate of the center. B squared equals 16. So B is 4. And so the co-vertices, I'm going to be adding and subtracting 4 to the x coordinate of the center. So it'll be at 3, 1 and negative 5, 1. Now if you know that we're going, I added 2 to the y coordinates, I added 4 to the x coordinates, so 2 is the rise of the slopes, I went up and down, 4 is the run. So I can tell you what the asymptotes are right now without drawing anything. The equations of the asymptotes will be y equals, and the slopes are 2 over 4 and negative 2 over 4, or 1/2 and negative 1/2, so plus or minus 1/2. And then for each one I'll have, times the quantity x minus the x coordinate of the center, so times x plus 1, and then plus the y coordinate of the center. So there's the equations for both asymptotes, one with a positive slope, one with a negative slope. And if you want to put them in slope-intercept form, you can. And then I can find the foci as well. C squared equals 20. A squared plus b squared, right? 4 plus 16 is 20. So C would be the square root of 20, which is 2 times the square root of 5. And just like with the vertices, I'd be adding and subtracting this to the y coordinate of the center. The transverse axis is vertical. So the foci are at negative 1 and then 1 plus or minus 2 root 5. And all this information I can now put on a graph. So center at negative 1, 1. Vertices at negative 1, 3. And negative 1, negative 1. Those 2 units above and below the center. And then 4 units to the right and left of center. 3, 1. And negative 5, 1. Are the co-vertices, and I got those now. I can make the little rectangle. Again, dot it. Don't make it solid. It's not actually part of the graph. And then through the corners of the rectangle, through the center of the rectangle, the asymptotes for the hyperbola. And this one's y equals positive 1/2 times the quantity x plus 1 and then plus 1. This one is y equals, the slope of negative 1/2 times the quantity x plus 1 and then plus 1. And I've got the vertices and asymptotes. I can make a rough sketch. There's my sketch, right? Make sure the curves are approaching the asymptotes as you go outward from the center. And then the foci are, again, somewhere above this vertex here, somewhere below this vertex. That would be at, negative 1, 1 plus 2 root 5, this one, and then negative 1, 1 minus 2 root 5. Again, you can figure out the units themselves. They'll be inside the curves, though, on the transverse axis. Okay. Again, the hardest part I feel there is getting the equation originally into standard form. Alright, I just got one more pair of these where I'm doing the same thing. Example 5 is one that's in standard form. Example 6 is one that's not. Alright, so I'm doing the same thing like 3 times. 1, 2, 3, 4, 5, and 6. Alright, so example 5, this is going to be one where the transverse axis is vertical. Right, the hyperbola should have a curve opening up and an opening down. And it's y squared minus x squared. The center in the x coordinate of the center would be negative 1. The y coordinate of the center would be 6. The value of a squared is 36. So a is 6. And because the vertices are above and below, I'm adding and subtracting this to the y coordinate of the center. Alright, so the vertices are negative 1, 12 and negative 1, 0. That was adding 6 and subtracting 6 from the y coordinate of the center. B squared is the other denominator, 16, right? So b is 4. So the co-vertices, I'm going to add and subtract 4 to the x coordinate of the center. We'll be at 3, 6 and negative 5, 6. Right, that was adding 4 and subtracting 4 to the x coordinate of the center. And I can tell you the asymptotes right now as well too. I went up and down 6, so this is going to be rise for the slopes of the asymptotes. And then 4 I added to the x coordinate of the center, right? That was left and right. This is the run. So rise over run, 6 over 4. The slopes are 3 halves and negative 3 halves. So y equals plus or minus 3 halves times the quantity, x minus the x coordinate of the center, so x minus negative 1 or x plus 1, and then plus the y coordinate of the center plus 6. And there's the equation for the two asymptotes. And if you want to put them in slope-intercept form, you can. And then c squared is a squared plus b squared, which would be 52. 40 plus 12, right? 52. So c is the square root of 52. 52 is 4 times 13, so that's 2 times the square root of 13. And this gets added to the y coordinates of the center, added and subtracted for the foci. So the foci is at negative 1 and then 6 plus or minus 2 root 13. And there's your foci. And I put all this information on a graph. Right, so you see, you should be able to identify this junk without actually graphing things. Hopefully with enough practice it becomes easier. So negative 1, 6 for the center. negative 112, and negative 1, 0 for the vertices, right? These are actually on the hyperbola. Then the co-vertices at 3, 6, and negative 5, 6. Negative 5. And then once I got those in, I can make my rectangle that contains the vertices and co-vertices. And then through the corners, make the asymptotes. And the equations for these asymptotes are this one's y equals positive 3 halves times the quantity x plus 1 plus 6. This one's y equals negative 3 halves times the quantity x plus 1 plus 6. Got the asymptotes in, got the vertices. I can draw my curves now, draw the hyperbola. Right, again, a rough sketch of it. And then again, the foci will be somewhere above this vertex, and then the other one's somewhere below this vertex, but the same distance on each side of the center. So this one I drew up here is at negative 1, 6 plus 2 root 13. The other one's at negative 1, 6 minus 2 root 13. Right. And again, if you want to go to Desmos, enter this equation, enter the equations of these asymptotes, and see that you got a proper hyperbola, go ahead and do that. Right? I did it for the first two. I'm not doing it anymore. I leave it to you. All right, I got just one final example, and again, I said it earlier. Got one there that was just in standard form. Here's one that's not in standard form. Right, and again, we have to do completing the square to put this in standard form. All right, so from the x's, I'm going to factor out a 4. Then we'll have 4 times x squared minus 2x. And I'll leave some space to complete the square. From the y terms, I'll factor out negative 9. And then you'll have y squared plus 8y. And then some space for completing the square. And then I'm going to subtract the 112 to get the constant term on the other side. Alright, now comes the completing the square. On the x's, I would be adding 1. But remember, 1 times 4 is 4, so I'm going to add 4 to the other side. And then y squared plus 8y, I'm going to add 16. Alright, now negative 9 times 16 is negative 144. So I would put negative 144 on the other side. Alright, so this may actually switch up on me because the other side is going to be a negative number. Alright, you'll see in a second. Just double checking here. Yeah. Alright, so on the left side we got some squares, right? This is 4 times, and then x squared minus 2x plus 1 is x minus 1 squared, minus 9 times the quantity, y squared plus 8y plus 16 is y plus 4 squared equals, and then negative 144, plus 4 would be negative 140, and minus 112 be negative 252. Negative 252. Alright, so that's actually going to switch these up. You see, when I divide both sides by negative 252, we'll get it in standard form. Now I'm going to switch these because negative divided by negative is positive, so we'll have the y squared term first with the positive coefficient, y plus 4 squared divided by, and then 9, negative 9 divided by negative 252 would be positive, and 9 goes into 252 28 times. 9 times 28, it's 180 plus 72, that's 252. And then the second one, the x's go second because you have a positive coefficient, positive 4 divided by a negative will be negative. Alright, so, and then 4 goes into 252 63 times. So this is x minus 1 squared divided by 63. Yeah, 240 plus 12, 252. Okay, and then equals 1. So there's the equation in standard form. Now I just need to make a rough sketch of it. Now once again, it's one of those where it's y squared minus x squared. So the hyperbola curves are going to be opening up and down. The transverse axis is vertical. All right, so the center, 1 for the x coordinate, -4 for the y coordinate. The value of a squared is 28. So the value of a is 2 root 7, right? The square root of 28, or the square root of 4 times the square root of 7. And once again, this is being added to the y coordinate of the center to get to the vertices. Right, the vertices then would be 1 and then -4 plus or minus 2 square root of 7. B squared is the other denominator, 63. And b would then be this, square root of 63, which is the square root of 9 times the square root of 7, 3 root 7. Alright, so that gives me to the co-vertices, which are not on the hyperbola. Right? And I'd be adding this and subtracting this from the x-coordinate of the center. So 1 plus or minus 3 root 7, comma, -4. And then once you know the vertices and co-vertices, I mean, you can tell me what the asymptotes are. Right? Once you know a and b, you know the asymptotes. Now, again, the value of a is the rise, right, because I was adding these to the y-coordinates. It's going up and down. The value of b is the run of the slopes. So 2 root 7 divided by 3 root 7, the root 7s would cancel. It's just 2/3, right? So one is a slope of positive 2/3. The other has a slope of negative 2/3, right? So y equals positive or negative 2/3 times the quantity x minus 1 and then -4, right? There's the equations of the two asymptotes. And then finally, c squared is a squared plus b squared, right? 28 plus 63, which would be 80 plus 11, that's 91. So c would be the square root of 91. Right, square root of 91. I'm pretty sure 91 is prime. No, it's not. 7 times 13. But 7 and 13 aren't perfect squares. Okay, so then we get the foci, right, which again, if I went up and down from the center for the vertices, I'm going up and down from the center for the foci. So I'm going to be adding and subtracting the square root of 91 to the y-coordinate of the center. So 1 comma and then -4 plus or minus the square root of 91. And yeah, then I'll just say graph here. You can do the rest. I'm not. Just plot the center, plot the vertices, co-vertices, make the little rectangle, the asymptotes, draw it in, draw where the foci are, right? This video is already over an hour long, and I've done 5 of these already. So once you have all this information, though, right, making a graph shouldn't be that much of an issue. Also, I guess just for some sense of peace and comfort, and help you relax, let me just go to the Desmos this one last time and graph these. So I'll graph these two equations, and you'll see that they're the exact same thing. Right? So 4x squared minus 8x minus 9y squared minus 72y plus 112 equals 0. And you see that there. And then I'm just going to put definitely hyperbola. And then I'll graph the equation we ended up with when we changed it to standard form. Y plus 4 squared divided by 28 minus the quantity x minus 1 squared divided by 63 equals 1. And you see it lands right on top of it. Right? Just turn 1 off and on, and it's exactly the same curve. Right. Wonderful. Alright, so yeah, so that was a lot, but I was doing the same pair of problems pretty much 3 times in a row. And I'm hoping that watching me go through these 6 examples here helps you out when you're asked to graph a hyperbola that's not centered at the origin on your own. And thank you very much for watching.